Welcome back to physics. Today we're going to ponder applications moving past lenses, and into our next application I want to introduce that with a problem. So let's consider light in water, incident on air, and then we're going to calculate the angle of incidence, or the angles of refraction for each of those angles of incidence. So looking at the boundary first, we have light traveling from water to air. Water, our index of refraction, 1.333. Air, our index of refraction, 1.000293. So we need to predict whether it's going to speed up or slow down, bend toward or away from the normal. When you go into or toward a substance of a lower index of refraction, then your light slows down. And in slowing down, it will bend away from the normal. So then drawing our ray of light here up towards the surface, passed it up a little bit. So we draw it up towards the surface and then we draw the normal in. Then our light is not going to get closer, but it's going to bend outward away from the normal. So then this would be theta r. This would be theta I. So we want to calculate our, sorry I wrote over the top of the flashlight there. We want to calculate our theta r value. So if we consider Snell's law, we are going from water toward air. N1 sine theta I is equal to N2 sine theta r. So our first substance being water, 1.333 sine, the first angle in part A is 20 degrees. So sine 20 degrees equals 1.00293 sine theta r. If we do the math and solve down for theta r there, we're going to get a value of about 27.12 degrees. Now in part B, we're doing a similar calculation, except instead of our 20 degree angle, we're going to use a 40 degree angle. So then we would be 1.333 sine 40 degrees equals 1.00293 sine theta r. Solving that down for theta r, we get a value of 58.94 degrees. So we started out with a small theta I, 20 degrees. We bent to a bigger 27. We went up to 40 degrees. We went to even a bigger 58 degrees. Now in part C, if we set up for an angle incidence of 50 degrees, I get 1.333 sine 50 degrees equals 1.000293 sine theta r. When we solve down for theta r, 1.333 sine 50, and then take 1.000293 and divide that, we're going to get sine inverse of a number that is larger than 1. If our larger is greater than 1, we're going to get a theta r value that our calculator basically says error or undefined. Okay, well, if it's undefined, thinking about what's going on here, our theta r went from 27 to 58. Our theta r is getting larger and larger. And in getting larger and larger, the largest theta r value we can have, if again I draw my normal in and I draw my surface here between water and air, as we continue to bend away from the normal, the largest theta r value I can get would be if that light bent directly along the surface. In other words, that theta r would be 90 degrees. If we try to push to a large enough theta I to go greater than 90 degrees, then we don't have a refraction taking place, because greater than 90 degrees would keep us down here in our lower substance, and then that would be a reflection. And that's what our application is here, something called total internal reflection. And I won't write that low on the screen. Total internal reflection. So, kind of the logic, you make your angle of incidence bigger and bigger and bigger when you start out in the substance that has the higher index of refraction. So you must have the light slowing down. You must have the light bending away from the normal in order to have total internal reflection occur. So let's kind of define it and develop the logic a little bit more. So total internal reflection. It is, first of all, internal. And internal, as we said, the light must start in the substance of the higher n value. And this is so that it slows down and so that it bends away from the normal, basically approaching 90 degrees. So then what occurs when you're at a great enough angle of incidence, which we're going to define, then what you get is an internal reflection, meaning that the light never leaves the substance that it starts in. This is a perfect 100% reflection. If you're at an angle of incidence less than that angle, then it will refract as normal. When you're at an angle of incidence greater than that angle, then it will totally internally reflect. So then our angle is the critical angle. And the critical angle is our largest angle of incidence in the substance of a higher n value, at which refraction will occur. So it's the cutoff between refraction and total internal reflection, and we will represent that as theta c. Okay, it occurs when theta r, your angle of refraction, is 90 degrees. So then mathematically, from Snell's law, n1 sine theta I equals n2 sine theta r. if we want to calculate the critical angle, then N1, the critical angle is your angle of incidence, theta C. That's going to be equal to N2 sine 90 degrees. That will solve you down for the critical angle. So it's not really a new equation. It's just recognizing what you need your theta R to be. Now, let's take a minute to look at this in simulation first of all, and then let's look at another example problem. So here's a simulation site. I've got one substance, a second substance, and I'm going to change our substances so they match what we just did the calculation for. We started at an angle of incidence of 20 degrees. We had our top substance being air at 1.000293. And we had our second substance being water at 1.333. Now, I'm going to take and flip these around because our light is starting out in the top substance. So you're going to have to imagine water on the top and air on the bottom because of the direction of the simulation. So now we've got a boundary between water up here and air down here, and we have our 20 degrees and the 27.12 degrees that we calculated. So it is bending outward, it is bending away from the normal. Now, as I increase my angle of incidence, watch what happens to the angle of refraction. It gets larger, it keeps going away, it keeps going away, out further and further and further. And we get a partial reflection up here. That's the 10%. But we're at 47.5 degrees for angle of incidence. As I go larger and larger, eventually, right around there, we reach the critical angle for water. And now what we have is a total internal reflection. All the light stays in our water. None of it goes into the air. This is a perfect 100% reflection. If we are less than the critical angle, then we get a refraction. But as soon as we pass that critical angle, which is somewhere between 48 and 50, okay, then we get total internal reflection occurring. You must start in the substance of a higher index of refraction. Now, let's take a minute and look at an example. And we have to give it a second to be able to bring it up. There we go. I'm going to make it a little smaller so I have some room. So, we want to calculate. We've got light traveling across a boundary between air and glass. If you have a boundary between any two substances, remember the conditions necessary for total internal reflection. You must start in the substance that has the higher N value. So looking at glass, looking at air, the crown glass has the higher index of refraction. So on A, our boundary must go from crown glass toward air. This will bend the light away from the normal and give us the opportunity for total internal reflection. In B, we want to calculate the critical angle. So then we're going to use Snell's law. Sine, or N1 sine theta I equals N2 sine theta R. But we want to put 90 degrees in for theta R. So plugging in our numbers, 1.52 sine theta C is equal to 1.000293 sine 90 degrees. Well, sine of 90 degrees is just 1. So then we're going to divide the 1.52 over 1.000293 divided by 1.52, and then take the inverse sine. And when we do that, we're going to get 41.5 degrees. Interpreting this, when theta I is less than 41.5 degrees, when theta I is equal to 41.5 degrees, when theta I is greater than 41.5 degrees. Sometimes you're going to get a reflection, sometimes you're going to get a refraction. Remember, the critical angle is the cutoff. So right here, when theta I is equal to 41.5, this is when theta R is 90 degrees. So theta R, that would be a refraction that's occurring. When we're smaller than that, then the light bends, it refracts into the air. When our light is greater, that's when we get total internal reflection. Now, we actually did a little bit of D there. Coming back to part C, we want to take and place the glass in water instead of air. Well, water has an index of refraction of 1.333. Glass is the 1.52. We know we have to start in the substance of higher index of refraction, so we're going to go from the crown glass toward the water. So calculating the critical angle here, N1 sine theta C is equal to N2 sine 90 degrees. So this would be glass 1.52 sine theta C equals water 1.333 sine 90. If we do the algebra and solve down for theta C, we're going to get a value of 61.28 degrees. So then again, we could do a similar interpretation as we did over here. Okay, if our light is incident less than 61.28 degrees, then the light refracts. Equal to 61.28 degrees, then we get a refraction at 90 degrees. Greater than 61.28 degrees, then we get a total internal reflection. Now, there are an incredible number of applications of total internal reflection, some that you use every single day of your life. We're going to move into making observations of total internal reflection, and then those applications, which will focus a lot around the technology of fiber optics. So hopefully this introduces the math to you, and we'll pick up with demonstrations and applications later on. Have a great day and ponder physics.